Okay, so dear students, this is very important thing how we can definitely compute the conduction band offset value, how we can compute the valence band offset value, and how we can compute the activation energy, and what is the role of activation energy. I just put it some significant remarks that if we will have lower activation energy, there will be higher recombination rate, and ultimately what happens, ultimately we will have performance degradations. So now I'm going to move on further so that I can add more positive information. Okay, now I'm going to talk about the role of both uh, positive valence band offset value and negative valence band offset value. Definitely, I have just explained about the mathematical equations like computation of valence band offset value and computation of the conduction band offset value, and same with activation energy. Now, if we have a negative valence band offset value, what will happen? Definitely, there will be band gap, poor band gap alignment, and there are basically two structures: cliff one structure and the spike structure. I need to explain about both these structures. Like if I'm going to talk about the cliff structure, if I'm going to talk about the cliff structure, normally cliff structure don't have any kind of barrier for blockage of opponent charge carriers, and we normally refer there is no blockage layer that can block the recombinational factor between perovskite or HTL or ETL with perovskite. And if we have positive valence band offset value, definitely what will happen, we will shift from cliff to spike structure, and in this case we would have a blockage layer that can significantly block the recombination rate of adjacent carriers. Like there will be a blockage layer between perovskite and HTL that will significantly block the recombination of electron with holes. So positive valence band offset value is one of the key point that normally improves our band gap alignment, that can suppress the VOC losses, that can improve the performance parameters. And if I'm going to talk about the conduction band offset, same methodology and same trend can be seen from conduction band offset value. Like if we have a conduction band offset value, there will be no blockage layer between tentative ETL and the perovskite. Definitely there will be recombination. Definitely there will be non-additive recombination rates. And if I talk about improved conduction band offset value, there will be cliff to spike structure, and there will be blockage between the interface of ETL and the perovskite that will significantly block the recombination of holes with electrons. And ultimately what happens, there will be lower non-additive combination rates. Ultimately, we will have better interfaces and better carrier extraction towards respective electrodes, either positive electrode or either from negative electrode. And ultimately, we will have improved VOC value with lower VOC losses, and the performance parameter will increase. So ultimately, we are going to focus how we can improve our valence band offset value, how we can improve our conduction band offset value. And in some way, somehow, we have improved both these values, we can definitely can address the poor band gap alignment issue related to tin-based perovskite. So next thing, I have just prepared a comparison, a difference between cliff structure and the spike structure, so that one student can easily understand what happens between two structures. So it is very important, and I have just put this information for more positive information addition to particular student. When we talk about the both structure, first one is basically structure and second one is spike structure. We know that we must change some way, somehow, our cliff to spike structure, and ultimately we need to think. First thing approach normally arises in our mind, we have to improve the interfaces between perovskite or ETL and the perovskite with HTL. So when we talk about the cliff structure, definitely cliff structure arises due to negative value or lower value of the conduction band value offset value and the valence band offset value. So what happens, we will have a lower quantum efficiency. Now I'm going to relate about the quantum efficiency, inverted power incident photon conversion efficiency, what is basically quantum efficiency, how it is related with the performance parameter. Definitely, when we have negative values of valence band, conduction bands, we could have poor band gap alignment, we could have more VOC losses, and ultimately what happens, the absorption capability of our perovskite will tend to decrease, and there will be low carrier generation, and there will be lower carrier lifetime and carrier diffusion length as well. Ultimately, what will happen, we will have lower quantum efficiency. Actually, quantum efficiency is kind of analysis that normally provides us information upon the incident light, how many charge carrier were produced. If we have better absorption capability, definitely quantum efficiency will be higher. In case of the cliff, we have lower quantum efficiency, and in case of negative valence band, conduction band offset value cliff structure, once again we will have higher recombination rate. I just told you, because we will have an energy of activation, energy for carrier will be lower, and ultimately recombination rate will be higher. We will have poor interfaces between HTL and the perovskite, and the ETL with perovskite. And third one, we will have lower potential voltage. If we will have lower potential voltage, we definitely have a lower electric field, and low charge between positive and negative electrode, and ultimately VOC losses will be prominent. Higher defect density normally will be increased in case of the cliff structure. Poor band gap alignment will happen due to cliff structure, and there will be no barrier for blockage of the layer. So these are the particular points. If coming to this one, we will have definitely advantages. It means what we have better absorption capability, we will have definitely better quantum efficiency, a lower recombination rate, because we will have energy of activation higher in case of valence band, in case of positive conduction band value, and there will be higher positive potential, lower defect. I'm talking about the defect. These defects are interfacial defect as well as surface defect, and ultimately we will have improved band gap alignment. If we will have improved band gap alignment, there will be more charge carrier capabilities, charge carrier capability towards their electrodes, towards their HTL, towards their ETL, with the lower recombination rate, and ultimately there will be blockage layer. So positively, we from this difference we can compute that both valence band and conduction band positive values are much favorable for us for making the structure more probated, the structure more less defective, and improve performance parameters. Now I'm going to talk about the LUMO and HUMO. These two terms are basically discussed many times in particular tin-based perovskites, and definitely if we have positive values conduction and valence band offset value, we could have better LUMO and HUMO values. Like I'm talking about, it has been seen that lower HUMO level and lower LUMO level, both levels normally creates a more performance degradation related to tin-based perovskite, related to lead-based perovskite, or in general in any perovskite. If we have a positive conduction band value and valence band value, definitely what will happen, we would have improved LUMO, and we could have improved HUMO values that ultimately improves the band gap alignment, and ultimately suppress down the VOC losses, and ultimately improves the performance parameter of our particular device. So one person need to think about that. What are the tentative strategies that need to be adopted while in designing some particular tin-based perovskite, while making our band gap alignment more effective and with lower VOC losses. Now in the last session of my video, so that I need to conclude my remarks. Definitely it's a lengthy session. Probably it will be tiring for one person to listen a lot of information, but particularly I tried to focus on the important areas related to the current progress, related to research gap, and in future work of the tin-based perovskite. So proposed solution, what is basically proposed solution? What is the end results? How we can propose a basic tentative solution, what will be the future work, and how we can address the gap. First thing, I believe so. As we know that conduction band value and the valence band offset value, both these values are being determined by the material properties of HTL and ETL. Like if we have some better additives that has better extraction capability of holes, better extraction capability of electrons that are being generated from the absorber perovskite layer with the lower recombination rate, definitely we could have a better performance parameter related to not only for tin-based perovskite, but also the lead-based perovskite as well. Like I'm going to talk about the second one, that I'm going to talk about the improvement of interfacial defects, interfacial recombination rate, or non-radiative recombination rate, or Shockley-Red Hall recombination rate. We could have an other possible solution, like we could place some interfacial layer between ETL and the perovskite, between perovskite and HTL, to improve the carrier extraction capability of generated electrons or holes towards their tentative HTL and ETL. That interfacial layer can be placed different positions, like first position, I told you this one, first position, and second, it can also be placed between a HTL and electrode, between ETL and electrode. But I believe so the suitable selection of interfacial layer not only can improve the carrier extraction capability, but also can passivate the defects related to surface defects, can also protect our surface of the absorber layer from relative humidity and the moisture as a passivation layer as well. So two important things are linked with the interfacial layer. First important thing is that we can have probability to get better carrier extraction capability towards ETL and HTL. We can have a passivation layer to protect our perovskite layer from relative humidity, weather, and external temperature like that, so that ultimately it can not only increases the efficiency, but it can also increase the stability of our perovskite device. And third thing is that we have seen that instead of usage of single ETL material like titanium dioxide, we could dope traditional ETL materials with lithium doped titanium dioxide, like ZNO doped with titanium dioxide. Like doping effect normally actually what this significant role plays. Doping can definitely increase the carrier extraction capability of our ETL more and can suppress our non-radiative combination. This could be the third important thing that need to be adopted, that need to be determined. Via doping, definitely doping can increase the carrier extraction capability of our ETL materials. And fourth one is basically we need to use front metal contact and the back metal contact with high work energy function. Like if we have poor work energy function for back metal electrode and front metal electrode, it will have poor carrier extraction capability towards its positive electrode and negative electrode. So ultimately, so we can say that we need to find some potential candidates with higher work energy function in order to have better carrier extraction capability towards positive electrode and negative electrode. And last one is the most important thing that need to explain before the end of today's lecture. So just I have explained that tin are extremely unstable to perovskite, and tin has very lower performance parameter as compared to lead base. So how we can improve the stability, how we can compete its optoelectrical properties with traditional lead based perovskite? The ultimate solution, I think so, is basically the compositional engineering. Like we need to use instead of single perovskite with the composition, like lead and tin mixed perovskite. It definitely can increase the stability. It definitely can address the defects, low defects. It definitely can increase the performance parameters. But important thing for being a research student, we need to find optimal composition of lead that can never harm human life, that can be implementable on large scale. For the theoretical point of view, it has been seen that the concentration for composition engineering for lead or tin mixed perovskite, it should be less than 50%. I believe so. 50% is very, very high amount that can be toxic. But from my point of view, I think so. If we try to design a perovskite with 25% composition with lead and 75% composition of tin, so that we could have better stability, we could have better performance parameter optoelectrical properties as compared to the control device. So the composition of 25 and 75% is possible in lab in simulation work as well, and it is very significant for the lab point of view as well. So I believe so today's session will be helpful for all the students who are just trying to find some gap, who are trying to find some key points, who are going to know a future direction. Thank you for listening me. Take care, stay blessed.